You are listening to Professor Megan Workman. Welcome to this lesson called Chemistry Lite, in which we will cover some basic chemistry concepts that you will need to understand in order for biology to make sense. These introductory chemistry concepts include the structure of atoms, how atoms interact to make bonds, some special properties of water that allow life to exist on Earth, and how to apply the pH scale to gauge how acidic or basic is an aqueous solution. And an aqueous solution is when water has something dissolved in it. An atom is the smallest unit of stuff or matter that retains its own elemental properties. And an element is a pure substance that's all made up of one type of atom. So there's gold elements, silver elements. These are pure substances that are made up of one type of atom. Some atoms you may have heard of because they're common in all living organisms include carbon, oxygen, nitrogen, and hydrogen. These four atoms are put together in various combinations, in various size molecules to perform different functions in living organisms like the human body. Here is a cartoon diagram of an atom that contains 4 subatomic particles in the middle with 2 additional subatomic particles apparently orbiting around the nucleus. This gives us some insight into atomic structure. All atoms, like this cartoon one, are composed of 3 subatomic particles, including protons, which have a positive charge, represented by the pink blobs here. And each type of element is defined, its identity is defined by the number of protons contained in its atoms. The green blob represents neutrons, which are equal to protons in size, but neutrons don't carry a charge. They are neither positive nor negative, they're neutral. The third subatomic particle that is important in our discussion today are called electrons, and they orbit around the nucleus of the atom. They carry a negative charge and they're so small that they're considered massless. Notice on this cartoon atom that the number of protons equals the number of electrons. This is common among natural atoms or atoms found in nature. This atom has no net charge because the positively charged protons are equal to the negatively charged electrons. There's 2 of each. Those charges cancel one another out, and so the atom has no net charge. Here is a periodic table that lists many of the atoms that have been observed in nature. And the number in each square represents the atomic number, or the number of protons in the nucleus of these atoms. So what element is our cartoon atom? It has 2 protons. So we look for the square with 2 protons and we see it's He. He stands for helium. So we know the identity of this mystery atom. How about this one? Count up the protons. 1, 2, 3, 4, 5, 6, 7. I see 7 protons. The atomic number is 7. So this element must be nitrogen. This is a cartoon representation of a nitrogen atom. We could go logically backwards. If I wanted to know how many protons are in the nucleus of a oxygen atom, I would find oxygen on the periodic table. Here it is, circled in red, and I notice that it has 8 protons. So oxygen atomic number must be 8. If oxygen's atomic number is 8, it must have 8 protons. Usually in nature, the number of protons equals the number of electrons. So the expected number of electrons of any oxygen atom is also 8. And how we determine the number of neutrons is we take the total atomic mass and subtract from it the number of protons. The bottom number in the periodic table square is the atomic mass. So for oxygen, the atomic mass is 15.999. Well, I'm going to round that up to 16. And that tells me that the number of protons is 8, the number of electrons is 8, and the number of neutrons is 16 minus 8 protons. That leaves 8 neutrons. Let's do a little more practice. How many electrons does a carbon atom have? 6. 6 because the number of electrons is equal to the number of protons, and since the atomic number of carbon is 6, well, that's the number of protons, then that must be how many electrons as well. For practice problem number 2, it asks how many neutrons a hydrogen has. So you could look at a periodic table in your textbook or online. It would give you this information that hydrogen has an atomic number of 1, but notice its atomic mass is also rounded to 1. 1 minus 1 means that hydrogens generally have no neutrons. There's simply one proton with one orbiting electron. You may have been wondering why the atomic mass has many digits, 15.999 for oxygen. This is because isotopes exist, and an isotope is when the same type of atom, defined by its number of protons, has varying number of neutrons in the nucleus of the atom. So this atomic mass number reflects the average number of neutrons observed among isotopes seen in nature. And it's okay to round this. 15.999 is close enough to 16 that for any quiz questions you may see, this is rounded up to 16. Now that you know the basic structure of atoms, our story can get a little more complex. We want to know how two different atoms might form chemical bonds and connect together into a molecule. And a molecule is just when two or more atoms are bonded together. Chemical bonds are determined by the behavior of electrons in the atoms. So we need to know where these electrons exist. For the purposes of our class, we're going to simplify the behavior of electrons in a way that allows us to predict how atoms will chemically bond together. So for the purposes of our class, we're going to imagine electrons existing in shells, nested shells around the nucleus of an atom. So in the nucleus of the atom, we have our protons and our neutrons, and then orbiting around this like planets orbiting the sun, we can imagine electrons. And each orbit out, because of its size and properties, can only contain a maximum number of electrons. The innermost shell, which we will call the first shell, can hold up to 2 electrons. It can hold 0, it can hold 1, or it can hold 2. The secondmost shell, second away from the nucleus of this atom, can hold up to 8 electrons. And the third shell out can also hold up to 8 electrons. More shells may exist, and we're not going to think about them much. We have a special name for the outermost shell of an atom that has any electrons in it. We call this the valence shell. So if the third shell of an atom had an electron in it, but there are no electrons in the fourth shell, and so on, we would call that third shell the valence shell. But the second shell could be the valence shell too if it was the outermost shell with electrons in it. That first shell could also be a valence shell if it was the outermost shell with any electrons. Atoms form chemical bonds in order to become more chemically stable. And I'm going to use the simplified terms of happy in quotation marks for a happy, chemically stable atom. So rules to make a stable atom are telling us where to place the electrons. So we're going to fill the innermost shells first and work our way out. So first we would put 1, maybe 2 electrons in our innermost shell. If there's still more electrons, then we have to start placing them into the third or the second shell and the third, and so on. The second rule for making a happy stable atom is to space electrons in the 4 directions: north, south, east, and west. Once north, south, east, and west quadrants have 1 electron, then you can pair them up until that shell is full. The fourth rule for a happy stable atom is that only full shells with paired electrons are stable. So any unpaired electrons tend to go seeking a mate. Let's see how this plays out in some cartoon diagrams. So let's draw an electron diagram of oxygen. Oxygen has 8 electrons. I can see that from its atomic number, which was 8. And I remember that the number of electrons is equal to the number of protons, so that's 8. So how I draw an electron diagram is I write the name or the abbreviation for the atom in the middle, so O for oxygen, and I start placing the electrons following the rules on the previous slide. First, I just draw an electron as a dot. North, south. Okay, so here are 2 electrons orbiting around an oxygen atom. That fills up my innermost shell. The innermost shell is so small that these electrons are considered paired, so I could also draw them like this. It's a pair of electrons filling the first shell. But how many electrons does oxygen have total? Not 2, it has 8, so we have to keep going. So here's 2, I have 6 more to distribute. So 1, 2, third electron, 4th, 5th, 6th, 7th, 8th. Noticed how I went north, south, east, and west before I paired them up. Now, you could alternatively put those last 2 electrons in any of the 4 quadrants, and it doesn't affect the stability of the atom. So here's an alternative way to draw that. Notice I've just paired the electrons, just for my aesthetic preferences, in different quadrants. But the thing that is the same in both of these is that there's 2, 4, 6 electrons in the valence shell. I could simplify my electron dot diagram to just show the valence electrons. And here I've done it. And here's an alternative correct way to do that. In both of these example oxygen dot diagrams, you would get full credit on an exam because you have the correct number of electrons showing in the valence shell. Here's another practice problem. Draw the electron diagram of hydrogen. Hydrogen has how many electrons? 1. So here's hydrogen. Easy peasy. 1 electron. Notice that hydrogen only has 1 electron, so it has 1 electron in its first shell instead of 2. Therefore, its valence shell is not full. This electron would desperately try to find a mate to pair with to fill its shell. So hydrogen is an unstable atom on its own. It travels looking to form chemical bonds so it can get a full valence shell. Let's see how that plays out. Oh, here's an empty space where another electron could pair up to make a happy hydrogen atom. This shell would be full with 2 electrons. But hydrogen has to make a molecule. It has to find another atom to bond with. So a molecule is when 2 or more atoms bond together, and atoms bond in order to fill their electron shells. We can predict how 2 atoms will bond together based on their electron dot diagram. So let's predict how oxygen and hydrogen would bond together. Here is our old oxygen dot diagram for its valence electrons. 2, 4, 6 valence electrons with 2 empty spaces where a couple more electrons could come in to fill this valence shell of oxygen. If it was placed in a bucket with a bunch of hydrogens, hydrogen also has an empty space. So what would happen between these 2 atoms is this unbonded electron from the oxygen would go to fill that empty void of the hydrogen, while the hydrogen's electron could fill the empty void in the oxygen right there. So that takes care of those empty spaces. And what we see is that then that hydrogen atom and the oxygen atom share those 2 electrons such that they're both more stable, and this forms a chemical bond there. But we have the problem of that other empty void on the other side of the oxygen, so another hydrogen can come in, fulfilling the same purpose over there. And that creates a very stable molecule that has 1 oxygen and 2 hydrogens. Do you know what this molecule is called? Water. So notice in the blue and yellow diagram towards the top of your screen, we have full valence shells on each hydrogen because they're sharing those yellow electrons in the diagram from their oxygen neighbor. Similarly, the oxygen atom has brought in 2 blue electrons from its hydrogen neighbors, and because of that sharing, there's a chemical bond that pulls those hydrogens towards the oxygen. Molecules can form bonds in 4 different ways that we're going to talk about in our class. We're going to call these covalent bonds that come in 2 flavors, polar and nonpolar covalent bonds, ionic bonds, and hydrogen bonds. The type of bonds that exist between 2 atoms depends on a tug of war for those shared electrons. It depends on if the atoms are similarly or have a similar strength in this tug of war. So let me explain more what I mean by this. The term used for the strength of an atom to tug on electrons when bonded is called electronegativity, and it depends on the atom's size and the number of missing electrons in its valence shell. Electronegativity has been observed and measured and given a number, and the number it's given falls on a Pauling scale. It's just the term we use for electronegativity value of each element. So each element has its own strength in this tug of war. So let's practice. We can predict which element has higher electronegativity if we have any 2 pairs. So for this practice pair, let's say fluorine and potassium. Which one has a higher electronegativity, meaning it would be more likely to try to steal an electron away from a neighboring atom? This ability to steal an electron away, called electronegativity, depends on the atom's size and number of missing electrons in its valence shell. Here's an electron diagram of fluorine. 1, 2 electrons in its innermost shell, 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. So here I can simplify it to our Lewis dot diagram of fluorine, where we notice there are 3 sets of happily paired electrons plus 1 unhappy single electron looking for a mate. And if it got its mate, then the fluorine would have 8 in its second shell. That would be a full valence shell for this fluorine. So if it gained an electron, it would be a very happy, stable molecule. Alternatively, the fluorine could get rid of 7, but it's a lot easier to pick one up than to get rid of 7. Let's compare fluorine with potassium. Here's a potassium. There's a lot going on, but notice in its outermost shell that has any electrons in it, there's only 1. So here is a Lewis dot diagram of potassium. It has 1 electron in its valence shell. It would like to lose that electron, and if it did, then it would have a full valence shell with 8 electrons each paired. So potassium needs to lose an electron, whereas fluorine needs to gain an electron. Knowing this, can you answer the question predicting which of these has a higher electronegativity, or which one is more likely to pull an electron away from its neighbor during a chemical reaction? Hopefully you said fluorine. And that is true. Fluorine has the highest electronegativity of any natural atoms. And when I say natural atoms, I mean atoms observed in nature. And potassium has a relatively low electronegativity value. And so what would happen in this interaction is that electron would be stolen away from potassium by fluorine. The type of covalent or ionic bond that is created during a chemical bonding interaction is determined by the difference in electronegativity that exists between the 2 atoms involved. So covalent nonpolar bonds have the least difference in electronegativity between atoms, or they could be an atom bonded to itself, so they have identical or equal electronegativity values. On the other end of the spectrum, ionic bonds are formed between atoms that have a huge difference in electronegativity. So if we do this practice problem, predicting the type of bond that makes each of these molecules, an H2O, an oxygen bonded to itself, O2, or a sodium bonded to a chlorine, NaCl, which is also called salt. Let's see. So I could look up the electronegativity values of oxygen and hydrogen. Notice that their difference is 1.2 on this Pauling scale. Oxygen, well, they have the same electronegativity because they're the same type of atom, so their difference is 0. And sodium and chlorine are very different, so their difference is 2.3. And chlorine has the stronger electronegativity value, so chlorine is going to want to pick up an extra electron, and sodium has a low electronegativity, so it's very happy to give one up. These this variation in the difference in electronegativity value between atoms in these bonds allows you to predict the type of bond that makes each of these molecules. So the oxygen bonded to itself produces a covalent nonpolar bond. The water molecule with the slight electronegativity difference between hydrogens and their oxygen neighbor produces a polar covalent bond. And the sodium paired with a chlorine with a big difference in electronegativity between those two neighbors produces an ionic bond. The fourth type of bond that we're going to talk about in our biology class is called a hydrogen bond. Hydrogen bonds are formed between two neighboring polar molecules. They're a weak connection between a slight positive end and the slight negative end of a neighbor, similar to two magnets lining up. So here we have a water molecule again. Because of their intermediate level difference in electronegativity between the oxygen and the hydrogen, there is an unequal sharing of electrons, where the oxygen with the stronger electronegativity has a greater hold over those electrons, and the electrons they exist nearer to the oxygen atom in the water molecule more of the time than they exist near those hydrogen atoms. This creates something called a dipole. A dipole is when within a single molecule there are slight differences in charge. This slight difference in charge is signified by this lowercase delta. That's what the squiggly d looks like, or that's what the squiggly d is called. And because the oxygen has greater control over the negatively charged electrons, the oxygen side of this water molecule is the negative side of the dipole. So notice the slight negative charge on the oxygen side. Whereas if we look on the opposite side where the hydrogens are not as strong in the tug of war over those shared electrons, and so they're giving up their electrons partially, and that creates a partial positive charge on the hydrogen side of the water molecule. Now this is happening in every water molecule in your bucket of water. So what happens between neighboring water molecules is that, just like magnets, the slight negative side tends to align toward the slight positive side of its neighbor. These hash marks that you see between the oxygen and the hydrogen here in the third panel, that represents our hydrogen bond. This hydrogen bond is holding neighboring water molecules together. It's not a very strong type of bond, but it's important for a discussion of water's special properties. Because of the hydrogen bonding that water molecules tend to participate in, they are very good at dissolving similar polar molecules. Therefore, polar molecules are called hydrophilic. Hydro referring to water, philic meaning loving, so water-loving substances mix with water. These are polar molecules. And an example of this is the vinegar in your salad dressing. Contrast that with non-polar molecules in which there is equal sharing of electrons within the molecular structure. This happens in things like lipids. Lipids are also called oils. And these things are called hydrophobic, meaning water-fearing, because they don't mix easily with water. And you can see this every time you've had to shake your salad dressing together to try to mix the vinegar and oil parts, because vinegar is polar, hydrophilic, and the oil is non-polar or hydrophobic. Eventually, the salad dressing separates into layers on its own. This property plays out in biological systems, and we'll talk about that more when we talk about lipids and biological membranes in a future lesson. We talked about non-polar covalent bonds, polar covalent bonds, and ionic bonds. We also talked about hydrogen bonds, and an example of hydrogen bonds is called cohesion, when two water molecules are connected to one another through those hydrogen bonds. Cohesion is a special property of water that contributes to the existence of life on Earth. Hydrogen bonds between neighboring molecules allow cohesion, which is when water attaches to itself, also adhesion, which is when water through these hydrogen bonds attaches to a neighboring substance that is not water. You may have witnessed this while measuring water, and here this is a graduated cylinder. You can see the meniscus of the water, which is the low point, is lower than the sides. Adhesion allows water to climb its way up the sides of the glass. Hydrogen bonds between neighboring water molecules also means that water has a high specific heat, meaning it has to absorb a lot of heat energy before it changes temperature. And these hydrogen bonds allow the solid state of ice to be less dense than the liquid state of water, which means that ice floats. And this is a special property of water that allows life on Earth because at the North Pole there is a giant floating sheet of ice. Now imagine if the opposite were true, if the solid state of water, ice, were more dense. It would sink. So it's very cold in the atmosphere. The water exposed to the air becomes ice. If that sank, then all of the water on Earth, all the oceans would be sucked up in this giant mound of ice at the North Pole, and there would not be water left to support life elsewhere. So we're very lucky that hydrogen bonds allow solid ice to float on top of liquid ice that exists below it in this northern ocean. Because of the hydrogens involved in creating water molecules, particularly in its liquid state, water is a great solvent. It's been called the universal solvent. It can dissolve a great many compounds. And related to that ability, aqueous solutions, meaning those in which water is doing the dissolving of other stuff, can take on different properties. And these properties, we call them acidic and basic properties. And acid is when there's a lot of hydrogen, positively charged hydrogen ions floating around in the aqueous solution. Oppositely, a basic solution is one in which a lot of hydrogen ions have been gobbled up, leaving a disproportionate concentration of hydroxide or OH negative ions floating around. And you can see that in this image of the pH scale. What you should remember about this for biology class is that the pH scale is measurable. It gives you a number, and that number tells you whether the solution is neutral, acidic, or basic. In the human body, most solutions like your blood are rather neutral. Most things that we eat are either neutral or a little bit acidic. There's not a whole lot of extreme bases going on in the human body. So that's one thing to remember. We like neutral or slightly acidic foods. The other thing to remember is that the scale shown here is logarithmic. It's not linear, meaning that if I take a step, I am getting 10 times more or less, in this example, acidic. So here a tomato is 10 times more acidic than water. But if I go 2 steps from a tomato to a glass of red wine, it's 10 times 10 or 100 times more acidic. So wine is 2 steps away. It's a pH 4 rather than a pH 6, so it's 100 times more acidic than a tomato. To review, what you learned in this lesson is that atoms are made up of protons, neutrons, and electrons. The participation in bonding of any two atoms depends on the electron arrangement in their valence shells. Electronegativity differences between two atoms define some types of bonds, the ionic, polar covalent, and nonpolar valent types of bonds. Hydrogen bonding is a fourth type of bonding that is important when we're talking about water. And you also learned how to apply the pH scale to gauge how acidic or basic is an aqueous solution. Low numbers on the pH scale indicate acids. Higher numbers above the neutral 7 signify bases.